Hello,
Thumbs up.
friends.
Hello, Mr. Stone.
Hello, Mr. Stone.
Oh, it's been too long since
Hello,
I've heard
Mr.
it.
Stone.
All right, I'm going to go ahead and click share screen so that you can see my document camera. Can everyone confirm that you can see my Angular motion sheet? All right, we got some thumbs up. Okay, so this top part is basically a key of formulae. I'm pretty sure that both the linear and the rotational versions of these formulae do appear on your equation sheet for the AP exam. Although now that it's online, I'm pretty sure you can just use whatever equation sheet you would like. But for the default one that I printed out for you at the beginning of the course, and for most of you 18 times since the beginning of the course, your equation sheet, I'm pretty sure has these on it. If not, well, here they are for your reference. Let's look at number 1. A pulley starts at rest and is pushed so that it accelerates. Good thinking would be to take phrases that give you an idea of your quantities and write the quantity. What is it telling you? Starts at rest means that we have an initial angular velocity of 0. And it is pushed. A push that makes something accelerate in the way that it turns is a torque. That's from the second video that we've done. So if that term torque does not seem familiar, a torque is a force that makes something rotate. Now, Maddie, I know you said you hadn't watched it. So here, you can still see me in the corner, right? Well, if I apply a force here, the whole pin just moves. But if I apply a force away from where I'm holding it, it turns instead. A force that is applied some distance away from a fulcrum, a point around which something would rotate, a force applied a distance away from that point is a torque. And a torque causes something to change its angular motion. And just like a force makes something accelerate, a torque gives something angular acceleration. So that is the briefest rundown of torque. But then we do get an acceleration. So there is an acceleration. Then it is allowed to continue spinning without friction. So we have a sudden torque, like an impulse, moment of impulse that causes angular acceleration. Then it stops and it just spins for a while. If there's no friction, it doesn't slow down. And if you're no longer providing a torque, it won't speed up either. So there's a brief moment of torque and then it just spins. Imagine a fidget spinner. You flick it, it starts spinning. Unless it has a reason to, it would spin forever. Usually friction will slow it down, but we're ignoring friction, so it continues spinning. And then finally, an object is placed against the pulley to slow it down. That gives it a negative acceleration until it reaches rest again, which will be our final angular velocity. So again, if you're trying to envision this, you're holding a fidget spinner, you flick it, it spins, and then maybe you move your finger so that it rubs as it spins, so it slows down until it stops. Which one of these graphs correctly illustrates that situation? We need to have it start out with an initial angular velocity of 0. Therefore, one of these can be eliminated right off the bat. Which one of these graphs could it not possibly be because it doesn't have the right initial velocity? Remember, you can hit spacebar to unmute yourself.
Right one.
the one all the way to the right side, this one. So this one cannot be it. No good. Arden. We've got two acceleration time graphs. But the thing about the acceleration time graph would be that the slope would give you jerk, which of course we try to ignore, or moment of jerk because it's angular. But we've got no information on this graph that would allow us to use those initial velocities. The area under the curve of one of these, under the curve area would be y times x. Acceleration is change in velocity over time. Move that time to the other side to multiply. And there you have. The area under this curve tells you the change in velocity, but it doesn't tell you from what it is changing. So here we have a positive change, it speeds up. Here we have a negative change, but this doesn't allow us to be sure that it is starting at rest and ending at rest. And in fact, even if this did start at rest, this one would not end at rest because there is more positive change in velocity than there is negative change in velocity. So there wouldn't be enough slowing down acceleration. There wouldn't be enough deceleration to stop it. So this one also cannot be the case. This acceleration time graph has a problem as well. Who can identify what the problem is with this one?
There's no negative at all.
There's no negative at all, so there would be no reason for it to slow down and come to a stop. This would be like if you were holding your fidget spinner, you flick it and it speeds up, your flick is over, so it's spinning, and then you give it another flick in the same direction so that it spins faster yet again. This one does not indicate any negativity, it doesn't indicate any slowing, it's not good. However, this one starts with an initial velocity of 0 that increases, that's acceleration. Then it stops increasing and continues spinning for a time with no more flicks, no more slowing down until it meets a decelerating torque, a negative torque, and it comes back to rest. This one is our best answer. Although this one, if it went on for just a little bit longer, would be the correct acceleration over time. Check it out. You got a positive acceleration now with no curve, so we don't have to worry about a jerk. Positive stops for a while. It's just spinning. Then there's a negative. If we extend it so that there is as much, those two little modifications of changing the axes and extending the t-axis would make it correct, possibly. But if we have to stretch it and make changes to it, it doesn't make it a right answer. At that point, we're just, playing with what's on the paper to make it worth having gone through the effort to print it out. But, there's something to be said for that, being thrifty and getting as much practice out of these sheets as is possible. Everyone comfortable with that one? If you are not, remember, if you want to ask a question privately, there is the option to send me one-on-one messages in the Zoom group chat. So if you are shy about having a question, feel free to send it via there. I won't call you out. But if you just want to ask a question out loud and you don't have any shame about it, just go ahead, unmute yourself, yell at me, and I'll help you out. All right, getting back to it. Number 2, using a motion sensor. God, I miss my motion sensors. I miss all of my toys in my classroom. Using a motion sensor, a student measures the angular acceleration versus time of an object. So we have acceleration time graph. That makes any slope would be jerk, and any area under the curve would be change in velocity. I think that it is worth reminding you guys the easy way to remember this. What graph tells you what? Position time. The slope is velocity. Velocity time, the slope is acceleration. The area under the curve for an acceleration time graph would be change in velocity. The area under the curve for a velocity time graph would be displacement. Same thing works with a displacement time graph that's angular. The slope would still be velocity time. The slope of that would still be acceleration time. Area under the curve goes up the same way. I know I showed you this at the beginning of the year, but this works too, and perhaps you've had enough time to forget it. It has been a long time, and kinematics was traumatic for most of you. All the brain damage you've experienced since then might have wiped out your memory. Number 2, though, using a motion sensor, we get this acceleration time graph. The graph is shown below. It's really shown off to the right. Which of the following correctly describes the motion of the object? All right. Well, we have no acceleration for a while, so there's no change in velocity for a time. Then there is a positive acceleration that lasts a small amount of time, a quick impulse. Then there's nothing for a little while. Then a larger negative acceleration. And some more time. Remember to think about that area under the curve. We've got this much positive area under the curve, that is positive change in velocity. And then that gets undone here. Well, I'm going to say that's probably enough to cancel it out. But if you look, there's enough to cancel out that positive change, and we have some left over. So it speeds up in the positive direction, which is counterclockwise is the positive direction because it says so. So it gets some counterclockwise speed, maintains it for a while, then it begins to slow down. Negative or clockwise acceleration when you're going counterclockwise will slow you down. It has enough to lose this change. If it started out with a speed of 0, which we don't, again, we can't find that from this graph, but if it started out with a speed of 0 radians per second, then it picks up some counterclockwise radians per second. This causes them to lose it. And in fact, right here, it is stopped, but it keeps decelerating, or negatively accelerating, really, so that now it actually has a little bit of speed in the negative clockwise direction. By the way, while I'm showing you guys tips and tricks, in your video on this, I mentioned a trick to remembering this. Clockwise is negative, counterclockwise. If the C is the negative, we've got negative, negative. That makes this positive, whatever. But it's actually just as apparent to figure out why that convention exists in the first place. Everyone remembers the unit circle, or at least remembers that there is a unit circle. This right here is typically referred to as our starting point, 0 degrees. This would be 90 degrees. If we take our displacement, our change in angle, from 0 to 90, that is in this direction, then our displacement is we gained 90 degrees. That's why counterclockwise has to be positive, or at least is conventionally thought of as being positive. If we went from 90 to 0 in the direction of a clock, then our displacement, we lost 90 degrees. So that's the reason that that convention exists. But perhaps I should just stick to answering the questions. Which one of these best describes what we've got? The object speeds up in the counterclockwise direction. Okay, it does that. Then it slows down. Well, yeah, it slows down when it gets to here. So they're not wrong yet. After some time, it speeds up in the clockwise direction, then slows down again. I see what they are doing. They're assuming, or at least the reasoning behind this would be that it speeds up in the counterclockwise and then comes back down, so that undoes it, right? No! Newton's first law tells you that you keep doing what you're doing until an acceleration happens to you. It accelerates, now it's got a new speed, it maintains that speed for a while. It's not going to have any reason to go back to its original speed just because the acceleration is over. So the idea that as this comes back down, it goes back to its original speed, this ain't that graph. This is an acceleration time graph. If this was a velocity time graph, then yes, it went up, then it went back down. This is an acceleration time graph. This is not the same thing. This one has to be wrong because they're assuming that they're writing it like this is a velocity time graph. The object speeds up in the counterclockwise direction. Yes. Then after some time, here's some time, it slows down. Okay. And then speeds up in the clockwise direction. That is rock solid. There's nothing that B says that is wrong. So I'm very sold on B, but of course there is a C, so let's read it just to make sure that it's not somehow righter or a better option. The object sits at rest. Already I'm skeptical because this is an acceleration time graph. It only tells me changes. It does not give me values of velocity. Iffy, but possible. Rotates counterclockwise at a constant speed. What? Then stops for a time and then rotates clockwise at, no, not, that is even less like reasonable than A was. At least A described a velocity time graph. B is by far the best one on that. We good on these so far? Give me some thumbs up emojis if you are feeling good. If you have any questions, again, you can ask them publicly or privately, depending on your shyness. Number 3. A student obtains a graph of an object's angular velocity, omega, versus time, and then draws the graph of the angular acceleration for the same time interval. Which of the following matches our velocity time graph? You just go through and say what's happening. We have rest. Not that we'll be able to see that on our acceleration time graph. We have a positive slope, that is a positive acceleration. Then we have no slope, that is no acceleration. Then we have negative slope, negative acceleration. Then we have no slope, no acceleration, negative slope, negative acceleration, no slope, no acceleration, and finally a positive slope for positive acceleration. And if this time, because it looks like that line's a little bit bold there, that would also be no acceleration because there's no slope. Which one of these matches it? Help me out, team.
The second one.
Second one, let's see. We've got positive acceleration, check. Then nothing, check. Negative, check. Negative, check. Positive, check. Absolutely. This one is the move. Very good, very good. This kind of coming back to you guys. I know we haven't seen motion graphs in a while, but it doesn't seem like you guys who are, responding to me have forgotten. We get to turn the page? All right. Here is the back of it. A horizontally mounted wheel of radius r is initially at rest. So we know that our radius is r, which is, I guess, 1 radian. Initially at rest means we have an initial velocity of 0 radians per second. And then it begins to accelerate constantly. Ooh, when you see that phrase, it's like somebody grabbing you by the shirt collar and screaming at you. It's like a neon sign with a siren blaring and flashing important indicators. What is it screaming at you when it says constant acceleration? Constant acceleration means that we can use what?
Kinematics.
Kinematics always work if you have constant acceleration. They never work if you don't. So we need to keep in mind that our kinematics are going to be helpful for this. Until it has reached an angular velocity omega. So now we know what our final velocity is. Our final velocity is a velocity omega. After 5 complete revolutions. 5 revolutions is an amount of what? Well, if you're spinning, and I'd say you spin around 5 times, I just gave you what? Dalton, you were tentative there.
Radians.
Yeah, it's an amount of radians. Radians are our unit to measure what quantity?
Our position?
Change in position, absolutely. Displacement. So we displaced by going around 5 times. And of course, we're going to want this in radians. 5 revolutions is 5 revolutions, not 5 radians. How many radians are in 1 revolution?
2.
2 pi. So 5 times 2 pi would be 10 pi radians. Anytime you have 3 properties or qualities in a kinematic, you can find a 4th. You just have to pick the kinematic that fits the 4 you are working with. So we have both types of velocity, displacement, and acceleration. Which one of these 4 has both types of velocity, acceleration, and displacement?
The 4th one.
The fourth one down. Absolutely correct. The one with no time. Final velocity squared equals initial velocity squared plus 2 acceleration displacement. Plug in and solve. Our final velocity is omega. Omega squared is omega squared. Our initial velocity is 0. 0 squared is 0. 0 plus anything is just whatever that anything was. So I'm not going to write it. Skip right to the 2. Acceleration, which is unknown, so we can't plug in for it. And our displacement, which is 10 pi radians. 2 times 10 pi would be 20 pi. Move to the other side. And there you have it. Of course, if you wanted to get this into radians per second, this would be radians per second squared. This is radians per second times radians per second. That's radians squared per second squared. Put a radian on the bottom, cancels out one of the square radians, so you get radians per second squared. So the units check out. This one is right. It's not the most satisfying conclusion. It's always nice to pin down a number. But again, working with formulae like this is a big thing for the AP exam. Or at least it used to be before they changed the AP exam to fit the apocalypse. We good to move on to the next one? Got some thumbs ups appearing. All right. An object moves at a constant speed. Constant speed means no acceleration, so we probably won't need to do any work at all now that I've read the whole problem. Constant speed means no... Wait, there is one kind of acceleration that you can have with a constant speed. You just have to change directions. Oh, maybe I do need to read the whole problem. All right, so our constant speed, and this is in meters per second. Meters per second is tangential speed because it's in a circle, so it's got to be tangent. So what does this look like if you are a visual person? Imagine we've got something spinning, and we are saying that a point on the outside at some point would be moving at 9 meters per second. And it has a circular path of radius 1/2 meter. That is 1/2 meter right there. So we know our radius as well. We're asked for the angular acceleration. Well, to find angular velocity, which is what you use to find angular acceleration, that times our radius gives us this. So our velocity divided by the radius would give us our angular velocity. 9 divided by 1.5 is what, 6? Yes. So our angular velocity is 6 radians per second, and it stays 6 radians per second. So if we take angular acceleration as final minus initial, then it's 6 minus 6 divided by time. Well, 0 divided by anything would be 0, unless, of course, it's a 0 on the bottom as well, in which case you would just not get an answer. So our angular acceleration is 0 radians per second squared because our angular velocity is not changing. There is, however, one kind of acceleration that this must have. Who can tell me what kind of acceleration this object would actually have? Not angular, because it's not changing the way it spins, but there is something that is changing.
Centripetal acceleration.
Absolutely correct, Dalton. It is centripetally accelerating. That is, it's being pulled toward the center. Why must it be getting pulled toward the center? Vector addition. It's pulled toward the center while going out, then it will begin to get momentum toward the center, but it's still pulled toward the center. So then there, and that's how you get it to go in a circle. So it does have a centripetal acceleration. But remember, that's like the acceleration of the tangential velocity. So that would be tangential velocity squared over r. So that end up being 81 meters squared per second squared divided by 1.5 meters. 81 divided by 1.5. 54 meters per second squared. But notice that is not an angular acceleration. We did not get an answer in radians per square second. Here I am extending the questions to make printing this more worthwhile for you. But you got to keep in mind that there is a difference between angular acceleration and centripetal acceleration. If it takes a bike wheel 3 seconds, that's an amount of time, to complete 1 revolution, it's a displacement. What is the wheel's angular velocity? This one couldn't get any easier. Especially considering we're working with pi, so we don't have to like solve stuff unless we want to. Velocity is the displacement over time. So it's going to be 2 pi radians in 3 seconds. It'd be 2 pi over 3 radians per second. If you are inclined to solve it, this drives math teachers nuts. Physics teachers don't tend to mind it. You would have to approximate it. So it would be about 2.09 radians per second if you wanted to solve it. Now, here's the, go ahead. You know you want to ask. No one has the guts to ask, which one do you want? I don't care. If you don't want to approximate it, you don't have to approximate it. But if it's a multiple choice question and all the answers are approximated, guess what you need to do? You need to approximate it to figure out which of those multiple choices is the best one for you. But if it's just freehand on your own work, if it was a short response, then it really ought not to matter. What is the angular velocity of the second hand of a clock? All right. Well, let's just do the same thing. We're trying to find angular velocity. In order to do that, we need time and displacement. What is the displacement of a second hand on a clock? Well, it goes around in a circle. So let's take a circle, 2 pi radians. How much time does it take the second hand to complete a revolution?
60 seconds.
60 seconds is completely correct, Kirk. So we just plug in and solve. Easy. So we get pi divided by 30 radians per second. Approximate if you feel so inclined. All right, guys. I'm going to give you a moment to do this. We're going to do one of those extension questions. I want you to do number 7 right now. And give me a thumbs up when you're done. But I want you to do number 7 in degrees per second. Again, you're going to redo it. But I personally prefer degrees to radians. So do number 7 again in degrees per second. All right, Kirk already got it. Maddie's got it. iPhone 2, Sierra has it. Maria's got it. Dalton's got it. Did you guys have the same experience with that? And Cassie's got it. That I did, where at first you're kind of like, and then you have like, it clicks. Like you almost feel like, you ever had to set your calculator from radians to degrees? You almost feel your brain having to switch modes, and then it clicks into place and you're like, oh, this one is exactly as easy as that one was. It just for a moment feels obscure. Let's redo it. We don't have to change the time. 60 seconds is how long it takes to go around. What is the displacement of the second hand in degrees over the course of 60 seconds?
160.
360 degrees. So it would end up being 360 degrees divided by 60 seconds. Get rid of some zeros. 36 divided by 6. 6 degrees per second. Easy. Once you make that mode switch. Last one on the angular sheet. A Ferris wheel takes 3 minutes for it to complete one entire revolution. How many seconds are in 3 minutes?
180.
180 seconds. And one complete revolution is a displacement. And notice that it only takes the passengers around one time. So we do only want to worry about one complete revolution. So that's going to be 2 pi radians. And we just want the velocity. Omega equals delta theta over t. It's another mode switch to pop back and forth between the Greek alphabet and Latin English alphabet. 2 pi radians divided by 180 seconds. Easy, easy, easy. Pi over 90 radians per second. It also, you could think of it as taking 3 times longer than the second hand of a clock. Therefore, we get 1/3 of the previous answer. 1/3 of, that means times, pi over 30 gives you pi over 90. These, honestly, I kind of feel like I should have given you a more diverse, maybe a 3rd page to this packet, because we just used the same equation 3 times. I probably could have given you a more diverse view of the angular world. So in order to make sure that you are as prepared for tomorrow's tiny quiz as is possible, strong recommendation. Maybe Google and try and find a couple more practice problems. Right? Like Varsity Tutors has a ton of solved practice problems. Like you can do it, then scroll down a bit and see the solution. It's really good if you're the kind of person who benefits from seeing a step-by-step. Again, Varsity Tutors, AP Physics, Angular Motion. Google that and it'll come up with the practice problems. So if you need a more diverse set of practice stuff, or you want to try using some of the other kinematics, give that a shot. Let's see what else. A couple of you have tried the Gizmo. I had a few of you ask for resets on the Gizmo already. But let's give the Gizmo a look together. I'll pull up explorelearning.com, and then I'll share my screen with you guys again. All right, if you can see that, give me a thumbs up. All right. It looks like out of third period, we've got 6 results at the moment. Fifth period has only 4 results at the moment. So maybe you guys need to get cracking on this. Perhaps you're waiting until this Zoom in order to give it a shot. So let's do that now. We have the ability to control the incline of a ramp in degrees, not radians. We have the ability to control the objects at the top. For one thing, we can drag them up and down. We can also change the shape, and we can change the material and the material of the object and the material of the ramp. So, we can see the coefficient of friction, which is a function of the material of the object and ramp. Remember, coefficient of friction always takes both objects into account. So we have a steel ring on ice. We have a block on ice. Just to cheat, we can see the coefficient of friction. A lot more friction on the block. Friction slows you down. So who do you expect to win the race, the ring or the block? Could you repeat that?
Ring.
You would think the ring with less friction. Anyone else want to place their bets before the race? Greyhound racing is illegal in Florida now, but not Gizmo racing, so you don't have to feel shy.
The ring.
All right. Well, let's see. And shockingly, despite having 10 times more frictional force, the block won? Well, there's got to be something else to this. This can't be right. We had 2 extremely bright people throw out that it had to be the ring that won. There must be some sort of cheat, something that we didn't take into account. Oh, who cares about a table? It's only recording data for one of them. Let's look at the energy graph. Oh, we've got all sorts of kinds of energy here. Right now, before I hit play, they're at the top of the ramp, so of course they have only potential energy due to gravity. They have had work done to bring them up the ramp. That work is stored in them in the form of their position at the top of the ramp. MGH, they've got potential energy. But when we hit play, they're going to begin to slide down the ramp. There's friction, which explains right here, energy lost. Well, why is energy being lost? That's how friction works. It takes energy out of something and slows it down. Translational kinetic energy, we know all about kinetic energy in the translational sense. That's just 1/2 mv squared. But kinetic energy wrought, kinetic energy, rotational kinetic energy. Translation is going down the ramp. So to get the center of this thing, to go from here, oh man, that doesn't help. To get the center of this to go down the ramp, that's translational. To get the center of this to go down the ramp, that's translational. So here would be the kinetic energy you would have for both. The lost energy, that's going to become heat or whatever. I shouldn't have to draw heat. But something that this guy has, this one doesn't, is the friction is also going to push back as it falls. That frictional force is applied to the edge of the ramp. The edge of the ramp is separated from the center of the ring by a small distance, just like I was showing you earlier with the pin. If you push on the center, it doesn't turn. You push on the side, you've got that leverage. That leverage causes it to turn. This wheel will turn and it'll pick up rotational motion. Rotational motion will give it rotational kinetic energy. So when we hit play again, did you see that growth? This one did have more friction. The box or block did have more friction, so it lost more energy due to heat. In fact, it had 10 times as much friction, so we had 10 times as much energy lost to heat. Makes sense. But for all of the kinetic energy that the ring picked up, it also picked up kinetic energy for rotation. So instead of all of its energy going to bring it down the ramp, some of its energy was going to make it turn. Turning doesn't help it go down the ramp. In fact, if you look, it was turning this way, which is directed backwards. So it should have slowed down a bit. So because the energy is not being used efficiently, it's not all going down the ramp, the block wins. Almost kind of like a quick cheat to it. All right. It is. I realize that our initial suspicions were proven wrong, but do you see why they were proven wrong and can feel kind of comfortable? Like, oh, okay, I get it now. Yeah, there was just a type of energy that we had not accounted for. If you want to learn a little bit more about rotational kinetic energy, then stay tuned. We'll cover that next week and the week thereafter. But if you are impatient and you want to delve into that rotational kinetic energy now, then College Board's YouTube channel has been going over that over the past couple of days. Yesterday's review was specifically about rotational kinetic energy. It was a pretty good one. So if you were going to pick a time to watch it, why not while it's fresh in your mind? Let's go back to the controls. And let's replace our block with a solid disk. Now this should be a little bit more fair, don't you think? We've got the same coefficient of friction because they're both rolling. We have the same material. We have the same ramp. We have the same shape. We have the same mass. The only difference is that this one is 1 kilogram and it is solid all the way through, whereas this one is a hoop or ring. So all of the mass is on the outside. Think about this for a moment, kids. Who's going to win this race? The ring or the disc? No bets now? I shook you too much with that last one. Now you're not confident anymore. Well, I'll give you a question. The whole difference between the block and the ring in the last one is that the ring rotated and that sucked up some of the energy that would have otherwise gotten it down the ramp. So whoever's doing the most spinning is going to lose this race. Everyone kind of dig that? Whoever's doing the most spinning is going to lose this race because they're wasting their energy on something that doesn't get them down the ramp. So the question is, which one of these will spin more easily? Which is easier to spin, a ring or a disc? Come on, give me a
A
bet.
ring.
Ring, right? You can take a ring and put it on one finger, twirl it around, and it goes around really easily. A disc, you got to like slap it from the edge, and it might take more torque to get it going. So if the ring spins more easily and spinning is going to suck up energy that would otherwise be used to help you win, the ring should probably lose this race too. All right, so that's my bet since you guys were tentative. And there we go. Because the ring was more easy to spin, you were completely right about that. It picked up more kinetic energy to rotate than it did to translate down the ramp. Let's watch. There you go. You see that the one that won, the disc, had more translational kinetic energy to get it down the ramp and less rotational kinetic energy to spin. Thus, it won the race. If I back out, we can see the questions. Give me, oh no, I'll pick for you. Let's look at number 2. One winter day, Lisa and Mary have a contest to see who can find an object that will roll or slide down an icy hill in their neighborhood the fastest. So Lisa picks up a sled and Mary finds an old tire. This is what we basically did up here. We got ice and we've got a ring of rubber, that's a tire. And then we have a block of wood that represents our sled. And for the reasons that we just talked about, of course, the sled wins. If Mary wishes to propose a rematch, what conditions would most favor the tire? So how can we game the system in order to favor the tire instead of the sled? Well, that tire is going to rotate. So how do we get its conditions to be more favorable? Who can help me out? Oh, we've got all these things that we can manipulate. At least give me something to try. If you're not certain, just give a suggestion.
What about changing the surface friction?
All right. So what do you want? You want it to be stickier, grippier, or do you want it to be slippery? Because we do have the option for frictionless.
More friction, like wood.
All right. Let's go for wood. So we got rubber on wood and we got wood on wood. Hey, Kirk got it. First try. The wood on wood is so grippy that the friction keeps it from sliding at all. So even though this would get less translational kinetic energy, this isn't getting any kinetic translational energy because it just straight up can't slide. There's too much friction. So having a nice grippy incline would totally favor the tire. What else could we change? Let's see, what else does it ask? So grassy hill versus icy hill. Well, as Kirk just showed us, which hill would be more likely to favor the tire? Grassy or icy?
Grassy.
Grassy. So we can get rid of C and D. We can't get rid of A or B yet. We need a little bit more information. So we know it's either A or B. And the difference between A and B, A assumes that a less steep, a flatter hill would favor the tire. B proposes that a steeper hill would favor the tire. Remember, the whole thing is that we're trying to game the system to keep the sled from moving. So what would get a sled to move? A steep hill or a flat one?
A steep hill.
Exactly. Right now, we've got a situation where the sled can't move because it's kind of flat, or at least flat enough to prevent it. But if we crank this up to 43, that is enough to reduce the friction. Remember, normal force times mu is friction. So when we turn this, when we get more incline, our cosine component, the normal force from the ramp, is going to drop. With less normal force, you'll get less friction. Or another way to think of it, a more vertical ramp makes you move vertically more. And, so going back to our options, our best answer is
A.
A. A less steep, grassy hill favors the tire. A steep hill favors the sled, and an icy hill favors the sled. So the opposite of steep and icy would be less steep and grassy. That's one down. You've got 4 to go, and you have until tomorrow at midnight. This is not strictly related to your quiz tomorrow. Your tiny quiz tomorrow is primarily on angular kinematics. So don't feel like if you're kind of stuck on the gizmo and needed a reset, don't think that that like has damned you from ever being successful on the tiny quiz. Tiny quiz is on different stuff. It's just I'm trying to cover all of these different subjects about rotation because there's a bunch of interesting things about rotation that are worth going over. But what will make an appearance on your tiny quiz, like one question, is torque. So I'm going to go back to sharing my document camera, and we will do one question off of our torque sheet. Any of you watch that video and get started on that? No shame if you didn't. I only posted it Tuesday. But have any of you given that video a watch and maybe started looking at this? Thumbs up if you're shy. All right. So it seems like you guys need to get on YouTube and give that one a view. Especially, I want you to have that done before we go into next week because I plan on building on the torque. Since you guys have not yet watched it, it would probably be beneficial to start with a conceptual thing about torque. Otherwise, I'm going to just be speaking Greek to you. As I said a moment ago, torque is a force acting some distance away from a thing's center of mass or fulcrum around which it would turn in order to give it angular acceleration. Think of a seesaw. If there's nobody on a seesaw, where do you put the mounting fulcrum, the thing that it turns over? Where do you put it in order to balance the seesaw? Or if you were trying to hold a meter stick on your finger without it falling off, where would you put your finger?
The center?
The center. The center of it is the center of mass because it's nice and uniform. Now, if we put a child on this side of the seesaw, and on the opposite side, we put, I don't know, a house cat. Which side of the seesaw will go down? Or in which
The
direction?
left.
Yeah, the left side, it'll go counterclockwise. Why? Because this weight, this force of weight, is greater than the cat's force of weight. But is there any way we can make the cat win this tug of war with torque? Is there any way we could game this system like we were just doing with the gizmo? Could we rig the conditions to have the cat's side go down and get clockwise
If you move
rotation?
the middle, like the thing that's holding it still, if you move it closer to the human, like the triangle.
Absolutely correct. If we give the cat more leverage, then the cat's side will have a greater torque. And you have just figured out the other aspect to torque. Torque, given by a lowercase Greek letter tau, and notice that it's lowercase, so it should be smaller than when you write a capital F for force. Torque is force times radius, which stands for the amount of distance here for the leverage. R really should be not radius, but lever arm or leverage distance, where R is the distance from the fulcrum to the force. So when we have the kid, even though they've got more weight, they've got a smaller lever arm, which gives the cat the advantage. Also, if you have it applied at an angle, this is 90 degrees, this is 90 degrees, so you get the entire force. But there is an angular component worth mentioning. So torque is for real sine theta. These are sine 90. Sine 90 is 1. So that is the briefest introduction to torque I think I can give you. Watch the video for more. But that is, I believe, enough to try this seesaw problem right here. If two masses, 50 kilos and 200 kilos, are on a seesaw of length L, where do you put the fulcrum to keep it level? Well, who can tell me which mass the fulcrum needs to be nearer toward?
M2.
Mass 2.
Mass 2, absolutely correct. Just like the kid and the cat, the heavier thing needs to have the fulcrum closer to it to use the change in leverage to balance out the change in weight. So if we draw this situation out, we've got 50 kilos G. So M1G weighing this side down. We've got M2G weighing the opposite side down, and they are L apart. Where do you put the fulcrum to balance it out closer to mass 2? But the question is, how close? How much of the length L needs to be from here to here versus from here to here? Solve using torque. Remember, torque, tau, force times lever arm, sine 90. If this seesaw is level, and of course weight always acts straight down, what is the angle between horizontal and vertical? I totally screwed that up. That should have said theta. I spoiled it, didn't I? It's a 90-degree angle. Sine of 90 is 1. But to keep it level, we need the torque going this way to be equal to the torque going that way. So if we have M1 on the left side, that would be our force, which is the weight, 50 kilograms times gravity turns mass into weight. Lever arm, I don't know, what do you want to call that? Well, this one's lever arm, let's call it R. Well, then what does that leave here? Whatever's left. So if this one has a lever arm R, then the lever arm for this one would be the length without R in it. So it would have a lever arm of L minus R. Sine 90 degrees. So the other side's torque would be 200 9.8 L minus R. Sine 90 is 1. Ran out of room. Did that process of setting it up, did I lose anybody? Be honest. You can send me a private message if you are afraid to indicate. But if I haven't lost anyone on that one, that's good, because this is stuff that you guys are for the most part, seeing for the first time. I haven't got anything pop up. All right. Then I assume you're comfortable. We can get rid of the sine 90 for being applicable to both. We can get rid of gravity for being on both sides of the equation and rewrite it 50 kilograms times R equals 200 kilograms times L minus R. Distribute this 200 kilos. 50 kilograms R equals 200 kilograms L minus 200 kilograms R. Do you see some like terms that we can combine? Which two terms can be combined?
The kilogram R's.
The kilogram R's, absolutely. When we move this 200 to the other side, this becomes 250 kilogram R's equals 200 kilogram L's. And then we are trying to find the relationship between L and R. So let's solve for R. I guess I got to use over here. That's fine. 200 kilograms L divided by 250 kilograms equals R. So we move this 250 to the other side. Kilograms cancels. Zeros cancel. What is 20 over 25? $20 over 25, people, come on. This is 4th grade fractions.
0.8.
0.8. So 0.8 L. So where do we put the fulcrum? If this is our 0 point, we need to go 80% of the length of the board and put the fulcrum there. And wouldn't 80% of the length of the board away from the child make sense? That would put it way closer to the, or I guess, I mean, it's not a child, but the mass 2. So that's how you do one of those problems. Again, it might be more satisfying with numbers, but there's more practice of this. I do, I think, 3 or 4 problems of this in the video. So if that wasn't enough to make you feel comfy and cozy with this, then check that out. And then you got a whole sheet worth of practice.
Would the one be on the quiz, like, would it be the seesaw?
Yeah, it would be basically like this. Either find the center of mass or do the seesaw thing. And torque problems that involve balance are easy. Torque problems that involve like it doesn't balance can be a little bit harder. But that's what we're doing next week, so don't worry about that now. We'll get there, and that'll be a new video for you guys to not watch. All right, that is all I've got, unless you have any particular questions, be they procedural or content related. Anyone got any concerns, comments, fears, hopes, dreams you want to share? All right. Well, then if everyone is good, then we'll call it here. We'll end the meeting. Remember to give that gizmo a shot. Give your 2 sheets a shot. If you haven't watched the video, give that a shot too. And while you're there, be sure to like, subscribe, hit the bell to receive notifications on my YouTube channel. Add me on LinkedIn so I can find a post-apocalyptic jog. I'm kidding. But we'll call it now. We've got the tiny quiz tomorrow. Should be pretty easy. It's on the service called Class Marker. So just check Edsby. I'll give you about 48 hours to do the quiz. Well, it'll be open for 48 hours. Once you open it, you'll have about 1 hour continuous to do it. And if you leave, then you have left. It'd be like walking out of class in the middle of a quiz, right? You might be thinking, oh, that kind of sucks. I'd love to be able to leave it and come back. Yeah, well, I can't take your phone and put up privacy screens when you're working online. So the least I can do to make this stuff harder to Google is to give you a time crunch. So you will, you'll have to start what you finish and finish what you start. You'll have any time that you have a 1 hour window within that 48 hour allotment, you can get it done at your leisure. You'll just click the link on Edsby, enter in the password that is on Edsby. You'll put in your name and student number so that I know it's you, and that'll be it. You don't have to make a new account. You guys have probably had to make plenty of new accounts for this e-learning stuff to work. Any questions about that process?
Are the tiny quizzes still going to be around like 8 questions, or are there going to be more?
Tiny quiz is still going to be tiny. 5 to 10 questions is the range. But yeah, usually around 8. So I don't plan on making them longer. Your tests are not really going to change either. It's not going to be terribly different than what you're used to. It's just going to be at a computer instead of at one of my tables with penises drawn on it. So for the full effect, you can draw a penis on your computer. All right. No other questions. I'm going to end it. Adios, team. It was good seeing all of you, or not seeing all of you, hearing from some of you. How about that?
Bye, Mr. Stone.
Adios.
Bye, Mr. Stone. Take it easy.
Have a good one.